Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everyone. We need to do this properly. How do we get... It's not very often we do it this way. Here we go. We did it. Wait, I can't hear you. Unmute yourself.
Can you hear me now?
Yes, we
Yes.
did it.
Okay. Hello, everybody, and welcome to another episode of Ask Us Anything About Electrochemistry. I'm Alex. This is my colleague Neil. We're doing this remote because we're just traveling all over the place.
Disparate locations.
Disparate locations, but we are trying to continue to do these live streams to answer all of your many questions about electrochemistry that we get through either YouTube comments or through phone calls, emails, webinar comments, things like that. And we are trying to answer or address your questions as best as we can. And sometimes a YouTube comment or even just an email isn't always the best way to really take a deeper dive into some of these questions. So we have this live stream, which is dedicated to answering some of your questions about electrochemistry. Now, in our over 60 episodes of doing this, more than a year of doing these live streams, we've observed that if you have a very, very broad question, you might not exactly get the best type of answer. It may be something that's more appropriate for, say, a webinar, with which Neil has many of them on our YouTube channel. And similarly, if you have a very specific question, we might not be able to answer it, such as what's the bond energy of a OH bond in, some kind of phenol molecule that I don't even know about. So questions that are kind of too specific, we might not be able to answer, and ones that are too broad, it's more appropriate for like kind of a lecture or a webinar. But questions that are kind of in the middle, some type of clarification on your experimental setup or on how a certain electrochemical concept works, are best suited for these types of live streams. Now, we aim to have this live stream go for maybe about 2 hours, from about 1 to 3 p.m. Eastern Standard Time. Of course, if you are watching this live stream after the fact, we usually try to put timestamps in the description below so you can find the question that might be most interested to you. I'm trying to think about all the other boilerplate stuff. If you're watching this, we also apologize in advance if we mispronounce any of your names. These are just YouTube accounts that are coming in, so you can put any kind of account name, and we might not be able to address it properly. And try not to spam the chat. We will try to get to your question as soon as possible. And I think with that said, we have a few questions that have already come in.
Yeah, well, let's get to those, and then I do have some that were asked actually earlier in the week. So as I tend to tell people with these live streams, I make this event each week, most weeks when we can do it, and it's on our YouTube, channel. And as we talked last week, which was a very riveting conversation about the ins and outs of Google and YouTube functionality. I still have not exactly figured out why YouTube allows you to make an event in advance of something, And the chat is there, so you can ask questions, you can communicate before the event. But like after a few days or so, the chats disappear. And I don't know why. So anyway, all that is to say that if you ask a question on one of our live stream events like this, but you ask it a few days in advance, I will record it and not lose it, but it won't appear in the chat anymore. So I do monitor this event in the days leading up to the live streams intentionally to make sure we don't lose questions. And so for those who asked a question on Monday, on Tuesday, Wednesday, whatever day, just know that I have not forgotten it, or I hope I haven't forgotten it. And so if you're not here live, you watch the replay to see the answer to your question you asked before. It'll be in the timestamp, and hopefully we don't lose those. But I if you did ask a question and for some reason a day went by and it disappeared, I don't know why that is, and I don't know how to get YouTube, the chat, to behave differently. I'm not sure why it does that. So that is all I can say about that. But I think for now we can try to answer the questions that are of the folks who are here live right now, and then we'll get to the ones that were from earlier in the week, because I'm not sure if those are here now. In any case, FCB asked, can I use a silver chloride reference for ammonia oxidation? And so generally speaking, I would say maybe. The problem is that ammonia and ammonium buffers and things like that can, I don't know how to, I think they can form precipitates with silver. Maybe there's an incompatibility there. Do you know exactly what it is?
Oh, if they form like, well, not.
Is it ammonium, like silver? Ammonium is a cation, so is it that ammonia does something with silver? I
don't know if ammonia will necessarily form a complex with alpha, but ammonia oxidation, some people do it in basic solutions. That's one thing. I do think just by itself, like in a vacuum, there's nothing unique to ammonia, but you do have to think about what's the solvent electrolyte, and whether that's going to like complex or form a problem with your silver chloride electrode.
When I was in graduate school, I used weak ammonium. What did I use? I had a synthesis process that used ammonia, so I used that. It wasn't electrochemical, that was a synthesis process. But I think at times I did a few experiments here or there with like ammonium chloride or ammonium sulfate of some sort, like some salt, right?
Oh, yeah.
And I almost always used calomel as my reference. So, for example, FCB continued as I'm not sure if there's a question or just saying what you're using, but basically, right, ammonium sulfate, I assume you mean an ammonium hydroxide, and so it is basic, right? Ammonium is it's a weak base, right? I think by itself, ammonia is a weak base.
Ammonia
NH3.
is NH3 neutral, and then ammonium is like NH4 plus, so it's a weak acid, I think, weak Bronsted acid, because it'll deprotonate the proton to do its acid thing. But then I think you could lose. I think so. I mean, you could also lose a proton.
Ammonia is a weak base.
Ammonia is a weak base.
It's a weak base. Yeah, it takes a proton away from water, leaving a hydroxide. So it makes the solution slightly basic.
Oh, okay. Yeah, so
ammonia
will be
it's a weak base, right? And some of that also comes from the fact that we try to generally avoid these kinds of electrodes with base, but like strong basic solutions. And so I think to your point, Alex, I do think it's like there isn't generally anything like specifically wrong, but there might be some incompatibility there. Is this best procedure to see catalytic activation of ammonia in an ammonia buffer? So just more about ammonia. I mean, I don't have a lot of experience with ammonia, like electrocatalytically. Like I said, I used it as in a synthesis procedure. Ammonia is useful for like hydrothermal synthesis procedures. You can put some transition metals and precursor materials in ammonia and boil it for a while, and it makes like transition metal oxides. So this is what I did when I was in graduate school. chemically, though, I mean, probably you just start with something simple like cyclic voltammetry or bulk electrolysis and just see if you have any sort of peaks. You could do pulse techniques if you want to clarify peak location, get rid of background noise, things like that. That's the sort of most general advice I guess I have for that, but I don't know if you have anything else to add, I suppose.
Yeah, I'm just gonna look up ammonia oxidation reaction.
Chris says too that ammonia will dissolve silver
to nitrate. Okay, so it can form nitrates and nitrites and silver nitrite, silver nitrate. Actually, silver nitrate is soluble.
Yeah, it's the only soluble salt of silver.
Solutions. But yeah, if you're going to form like NO2, that maybe ammonia will dissolve silver and come from a diamine.
So this might be part of it.
Complex.
Diamine. So maybe that's part of it too. Is that you might want to try to go with something like calomel or a mercury reference electrode. I think it might be a little more tolerant to ammonia. So that might be the case. But I think in relatively dilute situations, maybe it's not a big deal. But I like I said, I used a little in my experience with calomel. I think calomel is probably a better option. But yeah, so I think that's all we can give you on that. And yeah, I don't know a ton of specific information on ammonia activation or whatever. Again, it's one of those things. Your best bet is going to be try to find a paper in the literature and copy their procedure as a starting point, and then you can go from there, finding maybe something more specific, I suppose, right?
Yeah, I know. I think so, and I think your suggestion for cyclic voltammetry, just to see increased current. If you're looking at electrocatalytic reaction, vary the concentration of ammonia and see if you get more or less current at different potentials and things like that. That's usually the best way to see it, generally speaking. And of course, it also depends if you're looking at a homogeneous or a heterogeneous reaction. If it's heterogeneous, it's a little bit harder because you won't have any ability to control your either your catalyst or your substrate concentration will change, but you won't be able to do that with a heterogeneous catalyst. But generally speaking, the cyclic voltammograms for catalytic waves tend to be, it probably will be very irreversible. So one thing you might observe is a very large oxidation wave, but you get very little of the reduction wave back. So those are kind of the shapes of a voltammogram that will indicate catalytic activity. You won't get a return wave.
The irreversibility is a big thing, I think, yeah. I say we have questions from Ashish, and I think, if I'm not mistaken, Ashish, you were one of the people to ask a question earlier in the week. As I mentioned, I did catalog your question, though I also understand, I'll let you take over here, Alex. I just wanted to mention that I saw your question, Ashish. I did the thing that I mentioned before. I haven't lost it, but you appear to have asked at least the same question, which is helpful. Thank you. So we know that you're here and making sure we don't lose anything. And also, I think, as I said, Alex, you might have already communicated with Ashish to this point.
Yes. Yeah. So I can I'll share my screen and tell you a little bit. Ashish sent me some data. So can you see this? I know it's small.
Yeah, it's small, but yeah, we can see it.
Let me zoom in a little bit. This is some data that Ashish gave me of impedance. Now this is just average impedance magnitude, and then this is in DI water. And what he has shown or observed is that the impedance, it increases, but he's doing these time experiments where, to my understanding, every 2, 3, 4, 5, 6 minutes he's able to generate one of these spectra, and he's observing that from 2 minutes to 30, the impedance in the low frequency range is, I believe he says it's decreasing, but I actually cannot tell.
Can't tell with the color code here.
I can't tell with the color code, but I think, if we go back to his question.
It looks like the bottom is orange, and that's what it looks like to me on the plot. So I think it's going down.
Yeah, and he says that DI water. Let's see. Oh yeah.
Yeah,
Yeah, DI water
decreasing.
is decreasing, but then he had another one, and let me just share the other. Here we go. Let me just share the other one, and he was showing that this one, the PBS solution was I think this was decreasing as a function of time. And so all of these are, he's described this as like an interdigitated array. You have some gold electrodes, things like that. But he described it as a two-electrode system, and I thought this was something very kind of particular. That there are a couple of things I would say about the experiment. One is that it's a two-electrode system. I don't need to show this anymore. But it's a two-electrode system. So as you're doing AIS, the potential may be changing. It's not like you have a stable reference electrode. The other thing is that if you just put this interdigitated array in solution and you just start taking impedance very quickly, the system might not be stable. If you've ever taken the open circuit potential of a solution when you just put electrodes in, it's usually not very stable. It's not like a straight line. It tends to curve. It tends to change over time, over the course of minutes, even hours. And one of the things I told Ashish was you might want to let it sit for maybe 5 hours or so, and then do the same experiment to see if that trend is reproducible. Because from a pure scientific standpoint, I don't think there's necessarily a reason why the impedance would change as a function of time in just water or PBS solution. The value of the impedance certainly will be different between those two, absolutely. But the fact that it's shifting around is a little like, oh, I just feel like the system isn't really stable, especially if you're doing these measurements very quickly. Every 2 minutes, 3 minutes, 4 minutes.
He just clarified that they let it sit for 5 hours and the same trend repeated.
The same trend.
I mean, I think it. I mean, I don't know. I'm coming into this with less information than you because you've communicated, but I think one of two things is certainly true, or both, which is what Chris said here, is that you're getting ions in the DI water over time, possibly CO2 or some other gas. So that's a possibility, although I guess it doesn't. I could explain both because you might be slowly acidifying things if you're getting CO2. There's some foreign influence of foreign contaminant gas. Something is doing that, or as you were just describing, it's something to do with the lack of reference electrode. You have a shifting potential, and it doesn't matter how long you sit. There's nothing that guarantees you're going to reach a stable potential when you don't have a reference couple. It might just it might be sort of swimming around somehow forever. Right. And so all of these different impedance tests over 30 minutes being taken at a set point that's the same are really not being taken at the same set point, even though you think they are, because the voltage that you're picking, or the potential, right, open circuit or whatever it is not the same when the OCP is always changing ever so slightly. And so you're here at OCP, but as the OCP drifts, your set point is actually, unbeknownst to you, increasing or decreasing or something like that, because without a reference couple, it might not be what you think it is. So
yeah, and I guess it's strange because there's no like redox system, and the impedance is just the magnitude, so we don't have any phase information. But usually, as you go to low frequencies, you're picking up more capacitance. You're looking at the capacitive effects. And for the DI water, when you over time, it's like, well, it looks like the impedance is increasing by like thousands of ohms each time, and for the PBS, it's not changing very much at all, actually. At least that's what the impedance is looking like. So, but yeah, it's definitely a strange trend. I don't know. Your instrument as well is, I don't know, it's very old. I think it was built in like 2003, and when I tried to look up the instrument, it was discontinued by Keyence. So I couldn't actually look up anything about specifications and even like, potentiostat stuff. But, you also showed me just what a resistor on your instrument looked like, which was fine, but it was still a little bit noisy, and I don't know if that's also a setting as well. But I'm more inclined to agree with Neil's suggestion about like the OCP is drifting over the course of the experiment.
Yeah.
And that's changing things. And you are perturbing the system when you do EIS. So so even if you wait 5 hours, you changed it this time, you changed it the other time, each time you do it. So that's kind of strange thing.
I also wonder, just based on this last, he says that they created a PDMS microchamber. It has an inlet and outlet 1 millimeter in diameter, and the voltage is kept at 100 millivolts. So the voltage being kept at 100 millivolts is more to that point that it's 100 millivolts, but the reference is changing. So actually it's 100 versus something that's not steady. So what actual voltage it's at, so to speak, is unknown based on what we just talked about. And the other is that because it's so small and you're using a PDMS kind of microfluidic system here, diffusion might be a problem.
Yes.
The cell's so small that you might have some inconsistencies and diffusional effects, and you might be running into some of the trickiness that comes when you use like ultra micro electrodes and things. Smaller systems don't behave the way macroscopic ones do in terms of diffusional behavior and infinite plane kinds of assumptions and diffusion layers and stuff like that. So very generally, I don't have specifics per se, but just to say that if you're comparing your results, for instance, to conventional kinds of wisdom of diffusional, I don't know, properties or whatever, it might not exactly translate, right? Because your volume and your channels in a microfluidic system might not behave that way. So that's just one other point to make.
Yeah.
There's one back a little. I didn't want to miss it. There's a couple. I think this one from HEMA is the next one. What could be the reason in equivalent circuit by adding a separate element like a capacitor or a resistor with a Randles circuit? So in short, most of the time that you add an element with the Randles circuit, I'm just going to share my screen here. So for instance, if you have a Randles element, right? This is a Randles element, and you have your resistor and your capacitor. This makes a Nyquist plot that looks like that. It's supposed to be a perfect semicircle, but it's hard to draw a semicircle. Okay, so most of the time when things are added, to be clear, what is normally added is down. Am I thinking about this right? Yeah. Is something like really you'll add like a Warburg element. Okay, and so when you add in, I'm going to make it a different color so I can differentiate a little bit. And so normally when you add a different element into your Randles element, it's to account for when you have something like a diffusional tail in your data, right? I've talked about this in my webinar, for instance, where I go over the Randles, the Warburg diffusional kinds of things. a variation of this circuit, for instance, is where you can have a Randles element and then your Warburg sort of by itself. Okay. Practically and mathematically, there's actually some ambiguity for me. Both of these can end up looking almost exactly the same. And actually, I have never really quite been certain, to be perfectly honest with you, why you might pick one over the other. You tend to see this circuit more often, but you do see this one in the literature from time to time. And just to be clear, it's sort of like, why is it in the Randles element, or why is it not? Why would it be in the Randles element or separate? There's definitely some difficulty in answering that question, right? You can think about it practically, like for instance, the whether things are in series or parallel. If you work out sort of the microstructure of your electrode surface and you figure out what's happening, like sequentially or in series, right, or in parallel at the same time, sort of mechanistically, I guess. That's why we tend to think we use the Randles element. These are in parallel because we have a double layer capacitance on the surface of our electrode basically at all times in any liquid system, and then there's a charge transfer resistance for whatever process we're studying, and those are in parallel because like they're both there at the surface always. Like if you're doing some charge transfer process, some redox process, the double layer capacitance is like ever present. It's always there. It's not like they're both taking place in parallel at the same time at the electrode surface. It isn't in a series kind of function where it's like it goes through one and then it goes through the other. I'm not sure if that's the best way to kind of put it, but the other is that graphically what we see, of course, is that we see the evidence of the Randles element, because if it weren't, if it was one and then the other in series, that would look like this on our Nyquist plot. And so to a certain extent, the evidence of things being in parallel is looking at the Nyquist plot itself. But the other thing I'll add, I guess, is that we don't often put like another resistor in a Nyquist plot. That doesn't happen very often. The resistances are usually in reference to a charge transfer process, and we don't tend to represent those in that way, I guess. For each charge transfer process, we tend to add a distinct Randles element. But as far as a capacitor or a CPE or a Warburg element is concerned, we typically put it into our Randles element, and that's usually why we're adding it to again answer your question.
Actually, I'll add one thing just for people to be aware. There was a publication that came out not too long ago. It's an open access article from the ECS from Mark Orzum, of all people, on the proper use of Warburg impedance, and he goes through which circuit do you use? Do you use this one or this one? And all these other people are using my
question has been answered. Does he talk about which one and why?
Yes, and
I feel like this has never been addressed. Actually, I need to read this now.
Yeah, so the TLDR is this one. A is the quote correct one to use.
Yeah.
Mostly because it accurately represents reality, which is that, like, in order for there to be Warburg impedance, there must be an electron transfer, like oxidation reduction reaction. So this has to necessarily be the route, and this route, like this possible route, like going through solution resistance here, this cannot, sort of say, be the route. But he talks about this a little bit more. This just came out like 2024.
I've been waiting
something
a
like
decade for this answer,
that.
and finally, Mark
from
Orzum has
himself.
finally answered my calls that I have had about this. Yeah, put the DOI in the chat. Actually,
Oh yeah, yeah. Let me
Binero has
put the
asked for the
DOI in
DOI.
the chat.
I also want the DOI. Please give it to me.
Yeah. Let me.
Yeah,
Let's
that's.
see, DOI.
Is it so new it doesn't even have one? Sometimes it takes a while to get a DOI.
No, it should. I'm just always bad. Here we go. I'm just always bad at finding them on the website. Here we go. Let me put this into the chat.
Let's go
So
look.
that's the DOI, and that should take you to the paper.
Oh, I just found it too. Yeah, I simple
Yeah, you can also find it.
A simple
Yeah.
Google Scholar search finds it on the proper use of Warburg impedance.
Yeah.
Yeah, I'm
And,
definitely reading that after.
yeah, it's good. It's a short read. It's open access, so even us non-academics can actually read it.
Yeah, it is rare when we can actually get to some of the literature at the same level as the academics. So yeah, that's good. Okay. So that was Hima's question. Fred, I think, is next. Yeah. So Fred says, for galvanostatic electrodeposition, how do people calculate the current density they applied for their experiment? Does the current set in the software correspond to the current density already? Only if you have that setting in your software, in your software, I guess, your program. So most potentiostat software programs, to my knowledge, I mean, if you're doing a galvanostatic experiment like chronopotentiometry or whatever it's called, constant current, set current, whatever the software and the company calls it, you give it what current you want, it to apply for how long, and it does that and gives you the resulting voltage over that period of time. It's a very simple transformation to go from current to current density, right? I mean, you just divide the current by whatever your surface area is, and the only way that the current set in the software corresponds to the current density already is if the software itself has a way to enter the surface area as a setup parameter. So maybe some might, some don't, and then maybe they display the results as current density, something like that. But this is one of those things that if it doesn't ask for area, you could just make the transformation yourself by dividing your current column by area, right? So, and if not, I mean, right, if you're following a paper and it's like, I need 10 milliamps per centimeter squared, and you know how many centimeter squared area your catalyst is, you got to multiply that to get exactly how many milliamps to type into the program. Because if you put 10, it's not density, it's just current, right? So just knowing your units, I guess.
Yeah.
Let's see here. We got to get through. Where are we at? I think Vinay is next.
Yeah, looks like Vinay has a question. What is the physical significance of flat band potential in Mott-Schottky analysis?
Man.
We can talk about this. I know, Neil, you've been doing more research on it. But
I have. Yeah, Mott-Schottky. So I think we talked about this like a couple of weeks ago. I'm in the process of making very slowly. I've had a million other things to do as well, but I'm in the process of making a Mott-Schottky webinar. I can explain this in one way for you, and all I'm gonna say is that the way that I really want to explain it, I'm still working it out, which is why the webinar is not released yet. I'm very intentional when I do webinars about the content I deliver for you. All of the webinars that are on our YouTube channel, not to plug anything here in particular, I suppose, but I guess I sort of am. I'm very intentional about every slide and how I say what I say, and I'm very intentional about trying to make it clear and relatable when I'm trying to teach topics like impedance or RRDE or Kirschoff or anything like that. And I personally also sometimes have struggled grasping these concepts, like physically what's happening and all that kind of stuff, to the extent that when it's explained academically, as you'll often hear or read in a paper or hear at a conference, it doesn't satisfy. Like I find that way. I don't feel satisfied that like I understand the concept much better. So unfortunately, all I can really do for you is describe it in some terms of what I'm just saying right now, which is a way that might be a little less satisfactory if you're like me and you're someone who wants a really like clear, like non-sciency answer, as weird as that sounds. Like I really mean that. I actually really value trying to answer complex scientific ideas in the least sciencey way possible, because I think at the end of the day, all of us are human and we all want knowledge, right? If we're in this community of electrochemistry in particular, but science in general, we all want to gain knowledge. We're trying to understand the world better and these systems better and everything. And we all struggle from the same like human things. And for most of us, I don't know, maybe I'm just the dumbest one here, but I feel like for most of us, it's like just grasping what's happening in our mind really fully is how we get to a point of understanding it better. So that being said, I'll do my best, and if it's not as clear as I want or you want, my apologies, and I'm working on it. I will be having a Mott-Schottky webinar in the future that hopefully describes this more clearly. But basically what you have at any point, Alex, you know better these diagrams than I do. Please correct me if I'm drawing something wrong. In any material, you have what are called bands, which is basically like a probability of where electrons are going to be, right? And so these are sort of like energy levels or something like that, basically, right? So this is like an energy axis, and this is called the valence band, and this is called a conduction band. Okay. For a conductive material, these would touch. For a semiconductor, which is something you're doing Mott-Schottky on, there's usually a gap. That's called a band gap, and that's the energy difference between the conduction band and the valence band. Now, most of your electrons exist in this valence band. The conduction band is what is needed for electrochemistry, for conductivity, and so electrons need to basically make their way into here for it to be useful, so something like that. We have what's called the Fermi level, which is the energy. Is it always halfway in between? Is that just like standalone?
It's like the definition that people use. It's the probability where it's like 0.5,
right.
50%, you'll find an electron.
Right. And that's halfway between the valence band and the conduction band. Is that right?
For a non-doped semiconductor, yes.
Okay. Yeah, I know that with a doping, it'll move between there.
Move.
I'm just trying to be like the most baseline, right?
Yeah, so most basic.
Perfect. Okay. So basically, right, I'm just trying to get some definitions before we touch the band bending and what flat band is. So basically, the Fermi level is where 50% probability of an electron is between the conduction and the valence band. Now, what happens when you put this whole thing into solution? Solution, right, is that I'm gonna butcher this drawing. I'm not the best at drawing this. You get a bending of these bands one way or the other. I'm such a bad artist. I'm gonna try.
Don't worry about it. You get this.
That's supposed to be curved. Yeah. That's not bad.
Yeah, that's good. That's good.
Hey, I'm actually impressed. That's pretty good.
Yeah.
Okay, so essentially what happens is in solution you get this sort of bending effect where the energy levels bend just like that, and it's no longer this constant kind of a thing. The Fermi level will move depending on basically like the open circuit potential or the potential of your system, of your redox, of the process that's going on. And so the Fermi level, I guess, would move somewhere. Would it be still halfway between here, something like that? And so because these bands are bending, it sort of necessarily means that you can unbend them by changing the potential. That's what you're doing with Mott-Schottky in some sense, is you're adjusting the potential to interrogate the behavior of the conduction and valence bands. And in doing so, you basically get to a point where you reach where the bands are flat. That's what the flat band potential. So the potential at which like this sort of goes back to this, something like that. Did I describe that in some, is that kind of right, Alex, or do you have anything to add?
Oh yeah, no, I think that's right. I would
see the problem again. I hate what I described about putting it in solution where the bands bend and the Fermi level is fixed. What I said is not what I want to say. I want to say it better, and I can't figure out the words yet. Anyway, I'm working on it.
Yeah.
No. Like it's true, but it's unsatisfying. It doesn't physically what's happening. I can't wrap my head around saying it properly. But
yeah. So some things that make it kind of helpful, like so what physically is band bending is something that kind of eludes us most of the time.
Right.
But if you think about the energy level is like the energy level is an energy level as a function of like distance, sort of say. So when you see band bending, it literally means the potential energy or the energy level, the Fermi energy level at that point in space, like moving into and out of, away from the electrode, is actually different. It is changing. So actually, if we go back, we can actually just go back to that kind of that same picture. Let me see if I can. So if we go to that same kind of general, this needs to be thicker. We have the kind of same picture. We have the conduction band, and then we have the valence band. And yes, these bands can bend. It's a very interesting phenomenon when you have a semiconductor and you put it in contact with some kind of interface, right? Any kind of interface. It just so happens to be, so there's something called like a Schottky junction, which is when you have a semiconductor and a metal, right? Like when you put this in contact with a metal, these bands also bend. Yeah. So these bands will shift in relationship to, and I think this is also like the same way. So this is, I think this actually goes.
Yeah, it'll go up. Yeah, either way they go the same direction. Yeah.
They both go the same direction. And even the Fermi level, which I'm going to just draw here, so there's space. This also bends, which is to say that if this is the solid liquid interface, and like this is a liquid, then what happens is, well, the energy at the surface is different than the energy deep into the semiconductor. One thing I didn't realize about semiconductor electrochemistry is they don't actually like buy, like a piece of metal or like a piece of semiconductor that's like thick. They put like a super thin layer down. Like they actually don't have a whole, like this may actually be as thick as it is. And like the metal is like this big, it goes out all the way here. This is like your just metal, your conductor. So actually, I should write this here in case metal. Sorry.
Mental.
It is mental. This whole thing is super mental.
Definitely.
Metal. And this is like big. This is super big, but this is like microns thick. And then you put it in, at the interface. And one of the interesting things that happens in Mott-Schottky is that this creates like a, quote, space charge capacitance or space charge separation. There's, potentials are all based on like charge. So you can add charge, you can subtract charge, and we're literally changing the amount of charge inside the semiconductor that forces the energy to bend either to or away from what the Fermi level of your liquid is, which can be governed by, the Nernst equation, and if you have a redox species in here. So the flat band potential, like again, kind of the physical significance of the flat band potential, is the potential where the energy bands are flat. So maybe that's here, or something like that. And I think about it physically as the open circuit potential. Like that's what it is physically. It's kind of the point where it represents a reference point, sort of say. Because when you throw the semiconductor directly into solution, it may already be in like the bent configuration, depending on how it's doped. So you might want to, if you're going to do an experiment, you're going to do Mott-Schottky, and the bands are already bent way down or something, or they're very, very steep. You're not going to get a great, you're probably not going to get very good Mott-Schottky results. Like you want to do your Mott-Schottky experiment around the flat band potential. Like you want to find the flat band, and then you want to, do EIS around that flat band, where this is literally bending and wiggling back and forth around that spot. And so that's one of the kind of useful things about the flat band potential. It's just like a reference point when thinking about where is the semiconductor in relationship to the liquid, Fermi level, and stuff like that.
And what are the properties of the native semiconductor itself?
Yeah.
Finding its flat band potential is an answer to that question, basically. Mm-hmm. Like to give a comparison with other semiconductors, for instance, its properties near the flat band are more relative to its own properties and not its property in this particular system or what have you.
Yeah, it looks like Vinay has a follow-up, which we can look at. Does the cyclic voltammetry potential window of my supercapacitor material changes with changing the concentration? I have seen in many paper potential window is not changing, but changes in my case. Why? Let me think about this for a minute. The cyclic voltammetry potential window of my supercapacitor material changes with changing the concentration. In principle, no. It will look different, certainly. And I think it also depends what the concentration of your material is. Like in a lot of cyclic voltammetry experiments in just like pure solution phase, you're dealing with like 1 millimolar concentrations of like redox species. But if you have like a 1 molar concentration of a species, you have so much of it, that's going to help define what your potential window is. And if you go to like 2 molar, well, it's probably not going to change all that much. Even by Nernst equation rules, it'll still not change it won't change the window by that much. That's if I understand your question properly, but I might.
It also seems confusing to me because you're saying, it sounds like the question is, I change my concentration. Why is the potential window changing? As though the potential window is a dependent variable and not an independent variable. Mm-hmm. That's backwards. In other words, the potential window is something you pick. You don't measure a potential window. It's something you determine. So you might say, I'm going to go plus or minus 100 millivolts from OCP or so, whatever, right? That's my potential window. And then you're not measuring it per se. Like you know what I mean? You're not you're measuring the current as you sweep back and forth or something like that, right? But you're not measuring the potential window. You're setting it. And so, I mean, I guess fundamentally, I'm wondering if what you're saying is I change the concentration of my electrolyte from 0.1 molar to 1 molar, like you said, whatever it is. And then practically I'm determining I have to increase my potential window or something. Because it's not, again, it's not a measurement. In your software, you just put the same like starting and ending voltages for your CV, that is your potential window. What exactly is it you're observing that's leading you to think it's changing? Is my question.
Yeah.
And the only other, I don't know what else to think is going on, right? I mean, are you butting up against?
I mean, there may be some drift possibly in your reference electrode, possibly, because if you're sweeping to some limit, and all of a sudden you're seeing like a lot of voltammograms of like platinum electrodes in acid, they butt up right up to the hydrogen evolution negative potential range. But if there's a little bit of drift in your reference electrode, you go a few millivolts over, you'll start to see a huge change in your current, and you might think you've hit like the potential window, sort of say. So
Yeah.
that could also be another thing that you might be observing, possibly.
It could be other just parametric thing. Like if you have a fast scan rate and you have a really high concentration, the higher the concentration, the higher the current you get. And it might be that like when you scan really fast, sometimes it like takes a bit to flatten out. And so you need to increase your potential window to give it enough time, because it's like, oh, a little bit of current, it flattens out nicely. But more current, it takes a little longer and then it flattens. Like it's just more current, more double layer setting up or something. So maybe you just need to increase your potential window or slow down your scan rate a little bit, something like that. Might just be a practical kind of a thing, but I'm not 100% sure. Again, what you mean specifically, like I said, it sounds like you're measuring the potential window as though it's some parameter, and it's more of just whatever you pick it to be. So
there's a question before.
Yeah, Copernico had asked,
Yeah.
how fast do ions reestablish charge neutrality inside of a salt bridge of an electrochemical cell? I was wondering if it's possible to see a temporary Kirschoff current law violation. So just to be clear, Kirschoff's current law basically is that you have all the sum of charge going into one, like the sum of the charge is zero, right? Overall, the sum of the current, excuse me, is zero. So just to be clear, I think definitionally, the second part of your question is no, because current is a time-based unit. Current is the flow of charge or the flow of electrons. And so even if there is a time element in terms of like waiting for charge neutrality, it's still the flow of current or charge or ions, right, which is all the flow of charge, whether in electron form or ion form. There's a time-based element to that. It doesn't necessarily mean that it would violate Kirschoff's current law. It just means that the equilibrium is slow or something like that. But remember, it's that the sum of the current is zero. It doesn't mean that it can't be a slow or fast process. It could be any speed. But the sum is still, like, it takes forever for these two things to work their way, or they happen immediately. But it's still zero. It just one took longer than the other, but neither of those is a violation of the law itself. As far as exactly how long it takes, I think it's relatively instantaneous, right? As long as it's like a concentrated enough, because it's like a big long. This is my Lugan capillary triggering thing. It's like a salt bridge or like concentrated enough electrolyte is like a long bridge of ions all connected in solution, and they're all holding hands and connected to each other from one end to the other. I think we lost Alex here. He seems to be frozen, but I'll keep going, assuming that I am not frozen. I'm gonna leave him out until he comes back. Hopefully he just had an internet blip or something. But in any case, if you were waiting for one ion, for instance, to like move its way all the way down the salt bridge tube, that would take a really long time, because like an ion is really small. Locally it can be disrupted. Maybe, I suppose. Yeah, I mean, I think you might be right. I just in my mind, it's like speed is not necessarily violation of the law, but in any case, with the assumption of a salt bridge that's ideal situation, it's like it's a long tube maybe, but it's like highly concentrated electrolyte everywhere. For instance, you have an unbroken chain of ions everywhere, right? And so my presumption is that the charge continuum is relatively instantaneous. I think that the observation, if that isn't the case, could be drift in your voltammogram, for instance. Let me just say ions released from one side, ions released from the other side, depends on the ability of the bridge to move ions in the bulk. Right. On the bridge to move ions in the bulk. Yeah, but again, it's more about whether there's a continuous connection of ions within all of the parts that are there. And if that's the case, the charge neutrality is possible. Yeah, I mean, now I guess is there some practical limit? I mean, probably, like you couldn't have a salt bridge and a tube in the next state or country, and like there's some physical limit for these kinds of things, I suppose. But my understanding is that it's relatively fast, because let me sort of describe it this way. For instance, if you have a bunch of junctions or a salt bridge with your system, with your electrochemical cell, you might have a situation where you have a really high impedance, right? That can cause problems because there's a lot of ions, a lot of distance separating the reference and the working electrodes. The concentration of the ions might play a role here. Why no, that's exactly correct. And to what I'm saying, that's a similar situation, is that having a lower concentration or a really long tube is like having a really big resistor. It's just an added resistance between the working and reference electrodes, which can impede the progress of an electrochemical experiment. But it's still charge neutral. It's just highly resistive. And a violation in the first hundreds of microseconds, I mean, that is certainly feasible. I don't know. I really don't know practically. That small of a time frame is going up against not only the chemical phenomena of which you're describing, which could be the case, but also the ability of our electronics, for instance, to measure and monitor things. And Chris says, have you run EIS on? I think the problem that you would have, if there's a problem, for instance, Chris, is that the situation I'm describing, for instance, consider your ability to measure microseconds or something like that falls in impedance, which would be a good tool for measuring very, very quickly. On the other hand, a situation with a salt bridge and a high impedance between reference and working electrode means you'll probably struggle to get accurate data at high frequency as well. So you'll have competing forces. It might not work quite so well. But in theory, you could run impedance to try to integrate something like this. I'm not exactly sure what would work to prove or disprove like a charge neutral or not violation or something of that nature. It's at least feasible to me, Copernico, what you're saying is possible, which is to say there could be some brief time of like equilibration occurring, I suppose. Yeah. And only you would know, I suppose, how or if that phenomenon might impact whatever you're trying to study. But I suppose it is certainly feasible. Okay, let me find where we left off, and hope Alex will come back. I think he had some connection issues wherever he is. Let's see. Naveen has asked, what potential do I use to measure EIS for electric catalysis? This is a question that I think I've answered, not today, maybe last week or the week before. It's a question I do get pretty frequently, and it's becoming one that I feel like I'm constantly struggling to answer for one reason or another. Okay, let me put it this way. What are you trying to study with your electrocatalysis? What are you trying to study with your experiment in general? Some kind of redox process, charge transfer resistance, some capacitance, whatever you're trying to study. The second question is, what potential do those things happen at? And then my third question is, well, then what potential are you going to pick for impedance? Okay, so for some reason, I'm going to get on my soapbox again. I feel like I'm on my soapbox about this every week, but for some reason, with every kind of electrochemical experiment, cyclic voltammetry, bulk electrolysis, pulse techniques, or every kind of electrochemical experiment, we never seem to think about this question. We never seem to think, well, what potential, should I do? People will often wonder, what's the window that I should do CV? Okay, fine. That's a fair question, because you want to find the right potential to study, your redox process of interest. You might want to not go too high. You'll over oxidize something. Too low, you'll over reduce something. But people most typically tend to recognize that the potential that they pick for these experiments is around what they're trying to study. And if you're trying to do oxygen reduction and you want to do bulk electrolysis to produce a lot of product, you'll set the potential at minus whatever potential, and then you'll start reducing oxygen, right? -1 or whatever. And if you're trying to reduce oxygen, if you're trying to oxidize hydrogen, you'll put some positive potential, right? And for some reason, when it comes to impedance, all of this kind of wisdom evaporates. And I do not understand why impedance does this to people. It's such a tricky technique that people lose their faculties for reason. The answer to your question, what potential should you do impedance at, is the same answer as what potential should I do literally anything at. What are you trying to study? Are you trying to study this redox reaction that occurs at 500 millivolts? Then 500 millivolts. Well, I ran it at OCP. Okay. Does your redox reaction occur at open circuit potential? No. Then why did you do it at OCP? Because it's just the most common thing people do. Just think critically about what you're studying, what potentials are required for what you're studying, and then pick a potential to do impedance at there. That's it. It's as simple as that. It really is. Okay, let's see here. I think I've got through these questions so far. I want to get to the one that was asked earlier in the week. As I said, I wanted to cover everybody who's here live, though. So, okay, it looks like I have. So I have a little bit of a demonstration for this, so I want to get to this one. Earlier in the week, I see we have from Vaishnav VM, is a YouTube username, I suppose, so I apologize. But they asked, how do you calculate ECSA, the electrochemically active surface area, show the platinum method, and discuss other possibilities? So I want to do that with you. I think it's a pretty instructive type of demonstration. So I'm going to show you how to calculate the ECSA specifically for a typical sort of platinum catalyst, and then I will just kind of discuss sort of the process in general. I want to also pull up one paper, platinum. Where is it here? So here's a paper. So very briefly, The electrochemically active surface area is, I suppose, somewhat self-explanatory, right? It is not necessarily the geometric surface area, but it can be equivalent. But more often than not, we consider as electrochemists that if I have a material, the surface area of that matters or of interest is the one that's related to the electrochemical activity, right? Right, and it's not necessarily the same as just what's geometrically available. That could be due to other kinds of things like roughness of the material, different surface planes. And when it comes to platinum in particular, I'm trying to find the place in this paper where they talk about it. I can kind of show you, and I'll put the DOI for this as well if need be. Basically, what is done, and again, apologies, I'm just sifting through this paper. I'll pull it up actually while I do that, so you're not just looking at my face the whole time. So this is a very early paper where they were looking at some of the phenomena of electrochemically active surface area. Actually, this is the paragraph of interest. And so one of the things that's most commonly done for platinum is to take this number right here, 210 microcoulombs per centimeter squared. And so what I tried to do was kind of track down some of the earlier reports of where this number came from, right? Because that's one of the questions that is part of this, is that where does that number come from? How do we do that? And where it comes from are some, this paper's from 1971. There's some from maybe the late 60s, early 70s. I don't know what that, like, the first paper is, but essentially what people did is they got as clean, pristine a electrode as possible of platinum, and they knew exactly what it was. You know, we can do this now, but this is sort of the where this comes from, I guess. So, you know, whatever it was 50 something years ago, and they measured a voltammogram on this platinum, a catalyst or electrode, whatever, and they measured exactly this. They measured, roughly speaking, 210 microcoulombs per centimeter squared. So they had some area of platinum. They did a voltammogram and they got the area under the curve of current versus time. That gives you coulombs. And they said, for this particular ideal system, I'm measuring a certain amount of charge per surface area. And so this is like where we get this number from. Now, it's related to specifically what they're calling here this QH. So what was measured and what's used for the ECSA of platinum is the charge specifically related to the hydrogen adsorption desorption process on platinum. And then the other part of this is that it is taken predominantly on different according to the plane. So platinum has a 100 plane, a 111 plane, and a 110 plane. If my memory serves me correctly, I think the 110 plane is like the best one. The 100 plane is the least. Anyway, a lot of people, when they're studying like fuel cell electrocatalysis, something like that, I'm going on a slight tangent here, but often what you're trying to do is to maximize one of these facets in these planes because it's more electroactive than another, for instance. But what people are using as 210 is actually, as you can read here, it's a value justified on the basic predominance of the 100 plane, or an equal distribution of 3 planes. And so it's something like an average of, again, measured observable charge per surface area of platinum catalysts of various planes. And so when people are using polycrystalline platinum, as we most often do these days, which is just like a piece of raw platinum stock from a manufacturer, you cut it into an electrode material, or you get a flag of platinum, whatever it is, it's polycrystalline platinum. It's got some predominance of each of these planes. And so only folks who make, for example, single crystal catalysts where you can isolate one particular plane, they might be able to use a more specific number. But for the most part, people are using polycrystalline platinum. And so we use this accepted value of 210. Okay, so this is roughly where it comes from. So I just wanted to start with that. Okay, now the process, working from this presumption that we have 210 microcoulombs per centimeter squared of charge that is associated with platinum. We take a voltammogram, right, of platinum in like sulfuric acid. So this is a pretty common looking voltammogram of platinum. If you're an electrochemist, you probably recognize this kind of shape. In any case, you have several regions, sort of typical regions. You have this region right here. Let's see, it's kind of hard to see exactly. This region right here is the region of interest. This is the platinum adsorption desorption region, right? Here we have oxygen reduction. Here we have platinum oxygen, platinum oxide formation, and then this is its corresponding reduction. That peak is really, really large when you have oxygen saturated. When you don't, it's just the reduction of platinum oxides. And then if you go far enough positive, you'll end up with oxygen evolution. But basically what we're doing is we want to focus on this region right here, because this is where hydrogen is adsorbed and then desorbed. And we also have this region is very important because this is where there's the only part of a platinum CV where basically nothing is happening. This is just double layer capacitance. So what we're after, keeping in mind what I just showed you in the paper, is a charge associated with this process, just the hydrogen adsorption desorption region. And that means we need to we need to subtract the double layer capacitance, because remember, in a cyclic voltammogram, some charge, some current is always associated with the double layer. And so you don't want to include that. It'll make your measurement have some error. So I'm going to do this with you. I'm going to do this process and again show you how to calculate the ECSA. So what I need really is not the voltammogram. I need the current versus time, because this is current versus voltage. And if I get the area, it'll be watts. I need the area to be coulombs. So what I need is current versus time. So this is the current versus time plot. It's the same data. It's just current versus time for the same thing. Okay. So what I'll do is just kind of move to an area where I can see both the I'll point out what I'm looking at in just a second here. So this is select segments. Let me move this out of the way. Let me also make this a little thicker for you. Let's see. I'm gonna just make this a little bigger so you can see. And I just made one of them green and one of them red. So basically this green curve right here, right, is the top part of the CV. This red one right here is the bottom part of the CV. So this is the hydrogen adsorption region. This is the hydrogen desorption region. Okay, so what we need is the area under the curve of current versus time, because that's charge. So what I'm just going to do that, I'm going to add an area tool. Okay, and I'm going to adjust the points. I'm not going to fiddle too much with this, just to save some time, but I'll get it close to the number basically, right? And so here's roughly my area under the curve, right? And so you see what I'm doing is I'm bringing this up to this point here, because I'm taking out the double layer capacitance value. I'm just getting the value, if possible, of under the curve. Making sure my headphones are on. Make sure, Chris, say something if you can hear me. I appreciate it, just to be sure I'm still talking and not to nobody. In any case, the area under this curve here is about 63 microcoulombs. Sometimes what people do is add a tool under the other side as well. So what we do sometimes is we add another area tool under the other side as well. Let me adjust the points here and get it again where I'm after. Okay, something like this. And so you see these numbers are close to equal. Sometimes that's what people will do, is to check the I don't know what you call it, the efficiency of your experiment. So I've got 62 on this side, 63 on this side. It's roughly the same number. We can just call it 63 microcoulombs for good measure. You'll find different opinions about, oh, you should use the bottom part, you should use the top part, you should use the average of the two. There's various opinions, but basically this is the area we're after. Now, all we really do is a very simple calculation, right? We have 210 micro. So this is, well, I just converted it to coulombs. This is coulombs per centimeter squared, right? So that's the specific charge per area associated with this region. And what I measured was 63 microcoulombs. So this is cool. And I put it into coulombs. Coulombs measured, right? And so you can see if I just divide coulombs over 210 coulombs per centimeter squared, I get centimeters squared. So this is ECSA centimeters squared. So let's just get this looking general. Okay. And so actually this is an example where it's a perfect number. There's no reason that it would need to be a perfect number. In any case, in this particular example, I believe that the geometric surface area is something like a 5 millimeter disc, and so it's usually 0.196 square centimeters. Okay, so all this is to say that very often what you're doing when you're doing an ECSA calculation is you're getting a more accurate measure of the surface area as it relates to your catalyst's ability to do electrocatalysis, whatever your range is, right? And so in this case, what you're seeing, for instance, is that the ECSA is a little bit higher than the geometric surface area. And so quite often people will like to correct their current to be current density, but you have to know what your density is against, right? Is it with respect to the ECSA or the geometric area? This is another tricky thing that occurs with electrochemistry and research, for instance, because it's not always obvious. Sometimes people will be explicit in their I don't know, papers or their research. Oh, we calculated ECSA, and this is our current density with respect to the electrochemically active surface area. Sometimes it's just the geometric area, and sometimes these values will be the same, but sometimes they're not. And in cases like where you have very specialized nanoparticles or something like that, you can get a very high electrochemically active surface area as compared to the geometric area. And this is good. This means you have a very, active catalyst. Sometimes what people will do is they'll take the ratio of these two numbers, for instance, and there's a name for this. One of the papers I've seen talking about ECSA has a name for this ratio of ECSA to geometric area as it's almost like a roughness or some factor. In any case, if it's 1, they're the same, and if it's greater than 1 or less than 1, depending on the case, you can make an argument about how good or bad your catalyst is and compared to other catalysts. Okay, so that is basically the answer of how to calculate the ECSA for platinum specifically. The other part of the question, I think, was discuss other possibilities. To be honest, I'm not really aware of other methods specifically. And one of the tricky things that does arise out of this electrochemical method is that it is not always obvious how to calculate the ECSA for a different material, because platinum is such a well-known electrocatalyst that we have history. And this paper I showed you, for example, which again, I want to give the attribution before I move on. I want to make sure I'm giving this is from David Rand and Ronald Woods. Again, it's from 1971 in the Electroanalytical Chemistry and Interfacial Chemistry journal. And they were from Australia, from CSIRO in Australia. So I just wanted to give attribution of the paper that I showed you. But the point is, this is a well-known and well-studied kind of a system, catalyst. People have performed measurements. So the theory is that you could have if you're studying cobalt or nickel or anything else, all it would really take is some like similar experiment to be done, like a very idealized system, if someone has done it or if you do it yourself, of this is the material in whatever pristine form, I know what the crystal faces are or whatever it is, and this is how much charge I measured for this specifically known well-controlled surface area. You might be able to get a similar kind of specific charge or capacitance. And there might be situations out there where different materials, people have categorized that, but I don't know of any others that are as well categorized as platinum is. And so it becomes tricky because people are often talking about ECSA, and if it's not platinum, it's like kind of a black box. It's kind of hard to know. The only other thing that people will tend to do is to get a more accurate measurement, for instance, is they'll do things like BET analysis, Brunauer Emmett Teller, which is a way to it's a specialized piece of equipment, right? It's not electrochemical actually, but it measures the specific surface area of a material, for example, in like meters squared per gram, and then you know how many grams you have, so you know how many meters squared. So it's a way to get another measurement of surface area. It's really more specifically geometric, but in many cases you can sort of you can assume that it is equivalent to the electrochemically active surface area. Just double checking that everything is working properly here. Sorry about that. Having some technical issues today. Hopefully Alex ends up making his way back, but it looks like we're still running, so apologies here. Okay, so that'll about do it for that question. Hopefully that is a good explanation of the ECSA. And then I guess this is actually a similar question here from Naveen, is how do you calculate the charge in chronoamperometry? It's actually what I just showed you in my software here, but I mean, really it's calculating the area. So it depends on what software you're using, or if you're not using software at all, but let me kind of reset things here and show you again. But let me just getting this prepared for you. I'll share my screen again. Okay. So calculating the charge in chronoamperometry. So chronoamperometry is where you set the potential and you're measuring the current. And so what you're doing is measuring the current over time. And so in a chronoamperometry experiment, you have current versus time, which is what you see in front of you. Let me move the question out of the way. Right? This is the current axis right here on the y-axis. This is time on the x-axis. And charge, Q, which is measured in coulombs, is equivalent to di dt, or the change in the basically current times time, because a current is amps, which is coulombs per second, multiplied by seconds gives you coulombs. And so it's just an area. It's an area under the curve. And so realistically, if you have software that lets you do this, you can do it. Otherwise, you can do, it's called a trapezoid rule, where you add the areas up sequentially. But you're just getting the area that's underneath the curve. And it's just adding up all that area under the current versus time curve. And this, our software here is doing it automatically for you. You can see it's 431 microcoulombs in this particular case. It depends on where your baseline is, whether it's at 0 or it's right. It depends on where you're setting your baseline, but effectively wherever the area is under the curve of current versus time, you're multiplying the two axes together, you get charge. So that's actually just very specifically the answer for you. So hopefully that's helpful for you, Naveen. That's how you get the charge from chronoamperometry. There was one other question. Let me check too. I think Chris, do your instruments support running EIS experiments swept over a potential range? I think you're asking me, not answering for someone else. Anyway, so support running EIS experiments swept over a potential range, so CV sweep with a sine wave. No, that's not something that that we offer. That's actually something I guess I can understand from an interest, just a generalized interest. You know, could be an interesting thing. The tricky part, of course, is that if you're sweeping the potential and running CV, or if you're sweeping the potential and superimposing a sine wave, it's sort of not fundamentally impedance because you're not stable. It's not linear, the whole thing. You know, this gets into a bigger question of, okay, well, it's maybe an interesting like experiment to run, but it's not really strictly impedance. The best that actually most softwares typically do is you can set the potential, you can step, which is like what Mott-Schottky is, right? You set the potential somewhere, do some impedance, step the potential somewhere else, do impedance, step the potential somewhere else. So if you were to step fast enough, it's kind of like that, but really you're stopping at each potential. It's not a, you know, smooth sweep where you're also doing sine waves on top. That's not quite as common, although I suppose some people might do something like that in various applications. Let's see. Oh, I already did that one. Let me see here. So Naveen has some follow-up questions. If you go for FE test, efficiency, with chronoamperometry, it looks like you have two questions, but I think you're just clarifying. I think this is the second clarification. If you go for an efficiency test with chronoamperometry, the response would be a straight line. In that case, how would you get the charge? If you go for efficiency test, the response would be a straight line. I don't think I understand the question. No matter what you have for your plot, whether it's a straight line or it's a curved or it's something, the charge is still dimensionally the same. It's what I just showed you. It's the area under the curve. Physically, that's just true. Now, what that charge corresponds to, whether it's all related to this process or that process or whatever, is a whole nother conversation. But if you're asking, just strictly speaking, if I do chronoamperometry, if I set the potential somewhere and I measure the current, the area under the curve of current versus time is just definitionally the charge of that experiment. I said it wrong. It's actually the integration. It's the integration of that curve, right? That's the area under the curve. So I guess I don't totally understand, you know, why that in some efficiency test, I'm not sure exactly what you're referring to, but that wouldn't invalidate that calculation. That's still the charge of that kind of data. Okay, there was another question from earlier in the week, and it was a bit of a tricky one. I don't know that I can answer all these specific mechanisms, but Ishtiaq had asked, there are some conduction mechanisms for DC currents, such as Schottky emission, Poole-Frankel, Fowler-Nordheim, tunneling, and so on. And is there any similar model available for impedance spectroscopy? So just to be honest, right, I'm not familiar with these conduction mechanisms for DC currents. I don't know anything about these specific kinds of things. And so I guess it's sort of the question being, is there a mechanism similar for like AC method, like impedance? And all I can really say are, I guess, like two general things. The first is that the analyses from impedance, while there's certainly some, I guess, decent amount of exotic kinds of analyses that people do, in various ways. For the most part, the kinds of analyses that are done with impedance are circuit fitting kinds of analyses, right? And in doing circuit fit analysis, you'll get things like resistors and capacitors, inductors, diffusional elements, and things like that. Okay. And the second part of my question being, as it relates to conduction mechanisms, it's not exactly the same thing, but what I can kind of add, I suppose, to that discussion is that the conductive properties or conductive mechanisms in some respect are related to the impedance or the resistance, right? I mean, conductivity is kind of the inverse of resistance, and so with impedance, you're sort of you're measuring resistance, whereas with a DC technique, you're not exactly always measuring that. And so it might be that the answer to your question is something related to the impedance you measure fundamentally is like inversely related to conduction or conductivity. But if you're if you're looking for a more, I don't know, specific kind of a theoretical mechanism of like conduction or how it works or something like that, I'm afraid I don't know. I don't know any specific examples of that. There may be for sure in the literature, and I just might be ignorant of it, to be perfectly honest. Okay. Let's see, Naveen. Yes, following up here. How do we choose the potential to measure EIS for OES? So I think I already explained this, or at least I discussed this. Again, my answer is the same. What potential does OER occur at? What potential does HER occur at? You've just answered your question. This should don't overthink this. If you're trying to do chronoamperometry to study OER, what would you do? You would pick positive 800 millivolts or whatever potential it happens at, and you would study the current that's measured for the OER, and you would collect the products or something like that. So why would you do anything differently for impedance? It depends on what you're trying to study. Pick a potential that's related to what you're trying to study. That's the potential to do impedance at. It's really that simple. It's not some mystery, right? I don't know why impedance causes people to think differently about the potential that you would operate at, but think about it the same. Pick a potential that's related to the process that's under study, and then do impedance there. Okay, it seems like Alex unfortunately froze himself away, and sometimes that's the technical issues that we deal with when we're in different locations. But at the moment, I think we've reached the end of our questions. I'll just do a quick check to make sure I haven't missed anybody. But I think we got to everybody who's here asking questions. So we'll call it a day and a weekend, I suppose, right here. Thank you, everybody, for joining us for this for another episode here. As I said, I am working on a webinar on Mott-Schottky. It's going to be a little bit of time before I'm able to finish that. Have a number of other projects to be working on as well. So as always, I can't pump out webinars as fast as I'd like to, but I will get to it eventually. And I may end up repeating some other webinars like my EIS or my RRDE one at some point as I try to keep those fresh for people as well. In any case, in the meantime, we do try to keep doing these live streams every Friday, and so happy to see people here. And if there are any other questions, you can leave them in the comments below. There'll be timestamps of all the questions that we've answered today. And hopefully everybody has a great weekend, and we'll see you next time. Take care.